Start on with the discussion on the concrete data set. It's an exercise that we uh, gave all of you, and we'll quickly have a discussion on this right now. So once again, what you can do is you can log into Colab and you can access the solution file that I've already shared with everybody. So this is the data set, and you can see this. We have got all the different features of concrete: cement, slag, ash, water, superplastic, coarse aggregate, fine aggregate, age. So these are the 8 different features of concrete that we have. And based on the 8 different features of concrete, we are trying to predict what is the strength of concrete. Okay, so here we have the 8 different features of concrete. And based on the 8 different features of concrete, we are trying to predict what is the strength of concrete. So cement, slag, ash, water, superplastic, coarse aggregate, fine aggregate, age. So 8 inputs, and based on that, we are trying to predict the strength. So that is the output. So it is a concrete strength prediction that we are trying to do. It's a regression problem, and it will be a multiple linear regression problem. It's very interesting. So a couple of things that we have done in this exercise, you can see. So first things first, I've actually done a small pair plot of my data. So pair plot is a wonderful visualization technique which helps us to visualize the correlations between the different variables in terms of scatter plots. And along the diagonals, we are also able to see the distribution plots. So if you see the diagonals here, the diagonals are very clearly demonstrating the distribution plot of my data. So here you can see the distribution of cement, distribution of slag, distribution of ash, water, superplastic. So this is very similar to what I talked about a while back with respect to the histograms. So you can see the smooth histogram for all these variables. So you can clearly see the skewness. You can clearly see that some of the features are very symmetric, whereas some of the features like strength are a little bit right skewed. Okay, so this is a good scope that we get to now apply some pre-processing techniques, some transformation-based pre-processing techniques that we can apply now. Okay, now this is the correlation part that we are calculating. So we can do data.core, and this is how we can calculate the correlations. So when I do data.core, what happens is we can compute the correlation between the different set of numerical variables, right? So we have got 8 features, and we can compute the pairwise correlation between every single pair of feature. So this is how we can compute the correlation. So we can basically compute the correlation between every single set of feature. Okay, so the correlations we can compute, and we can also visualize the whole thing in the form of a heat map. So we can create a heat map, and we can visualize the whole thing in the form of a heat map. So that's the visualization that we are doing. And if you see right now, what are the key takeaways from this particular heat map correlation visualization? So we can clearly see that strength is the output. Strength is what we are trying to predict. And we can clearly see that cement is the strongest predictor of strength. So out of all the features, we can see that cement is the strongest predictor of strength. So cement is the strongest predictor of strength. That's the inference we are able to make out. Okay, so out of all the features, cement has the strongest correlation, 0.5, followed by superplastic, followed by age. Another very interesting observation that you're able to make out here is that none of the features are exhibiting a very strong relationship. Unlike the data set on advertising, you can see here, all the features are having moderate to weak correlation. None of the features are demonstrating a very strong correlation. So even the cement feature, if you see, is having only 0.5 correlation, which is very low. That means if you take individual features here, like what we were doing in the advertising data set, here if you take individual features, if you try to build a model only with cement, if you try to build a model only with plastic, super plastic, coarse aggregate and all that, you will get a very low R squared. The R squared of the model will turn out to be very, very low. So that is another very important concept to be kept in mind. Next up, we are just building the regression model. This is something everybody has done. You have split your data X and Y. And this is the code that we have used, data.drop. We are dropping the strength column, and everything else is basically part of my X, and strength is part of my Y. After that, linear regression, model.fit X train Y train, and you're finding out the coefficients and intercepts of the model, and this is the R squared scores. And you can clearly see that the iteration 1 linear regression model that we are getting is giving us around 60% of training accuracy and around 60% of testing accuracy. And as I said, I'm using the term accuracy and R squared interchangeably. So we can say that yes, R squared of the model is 60%, which is kind of an underfit model. So to start with, we are getting a highly underfit model. The R squared of training and testing both are very, very low. And there is scope to make it better. We can build a better quality model. What is the reason why the R2 scores are very low right now? The reason is because the patterns in my data are non-linear. If you look at the real world data patterns, the patterns in the data are extremely non-linear. Okay, so the patterns in the data are highly non-linear. The overall patterns in the data are highly non-linear. And what we are trying to do is we are trying to build a linear model on this data. So despite the data patterns being highly non-linear, we are trying to build a linear uh, model on this particular data. And hence it is coming out to have a very low accuracy overall. That's the inference. We talked about cross-validation yesterday, and cross-validation is the idea where we don't want to judge the model based on a single test accuracy. Rather, we want to compute 10 different accuracies and take the average. That is the whole idea of cross-validation. So, instead of relying on a single accuracy score to evaluate the model quality, we compute 10 different accuracies and evaluate the average cross-validation accuracy. So that's what we do. We get 10 different accuracies and take the average score. That's what we do as part of cross-validation. The second idea that I wanted to clarify here is we can see that if you remember, we saw that in the original distribution plot, a lot of features had a substantial amount of skewness. When we looked at that distribution plot, we saw that there were some features which were right skewed and there were some features which were left skewed. And we also discussed a little while earlier in the discussion that skewness is a bad thing. Whenever your data is skewed, in this case, we have certain features, right? So whenever we have skewed features, the model we end up building will also be skewed. So this is a real problem that we are facing right now. So if you are working with skewed features, which we have in this case, and if you are using this as part of supervised learning, the model will also be highly skewed. And that's the exact problem that we are facing right now. We are dealing with a highly skewed model here. Okay. How do we correct the skewness? What is the way to resolve the skewness? How do we mitigate the skew? How do we reduce the skewness in the data? We can use something called a power transformation. We talked about this discussion. We discussed about this, that where if we have skewed data, if we have right skewed data or left skewed data, then the supervised learning models will end up being biased. Okay, if you have outliers in the data, then the model will not learn those outlier patterns that well. It will learn the other patterns very well, but especially for cases where some values are very high, some values are very low. Like we took the example of salary. Salary is a right skew distribution. So if you have a right skew distribution kind of data, then if there are very high salary values, there are only few people in the company that make high salaries, right? So if you're building a supervised learning model on that data, then the model will not learn those patterns well because there are not enough examples to learn from. Okay, so maybe somebody in the 3 to 5 lakhs bucket, there are a lot of employees in that bucket. So the model has enough examples to learn from. But especially somebody in the plus 20 lakh or the plus 50 lakh bucket, the model will struggle because there are not enough examples to learn from. And how do we correct it? We use something called power transformer to reduce the skewness. We can make the distributions more symmetric and more normal. In case you are wondering what is going on behind the scenes, mathematically, power transform uses something called a Box-Cox transform. We use something called EO-Johnson transformations. And these are all different types of mathematical transformation techniques. These are all part of data pre-processing. So we take the original data and we try to apply different types of mathematical transforms like log transform, square transform, exponential transform, all of these kinds of numerical transforms we try to apply on our data to make them less skewed and more symmetric. Next up, we are going and applying the gradient boosting, which again, most of you have done. And you can clearly see before that, as you can see, with a baseline linear regression model, we were getting 60%, which all of you reported. And moment I apply power transformer and do linear regression, you see this 80%. I think this part, some of you did not do, but this is the improvement I wanted to also highlight, that the moment you correct the skewness in your data, the moment you reduce the skewness in your data, so after pre-processing, when you build the same linear regression model on the same data, see how the scores have become better. So we are getting a more robust model and a more accurate model after we apply power transformation. Okay, and this is the comparative understanding I was clarifying yesterday. So I was telling that, okay, whenever you evaluate a model, it's always on a comparative scale. So iteration one, what were the training and testing scores you were getting? And iteration two, how did the model improve? So did the training accuracy become better? Did the testing accuracy become better? So do we have a better model compared to what we had before? So that is how we evaluate these models. Okay, and this is with gradient boosting. Gradient boosting regressor is the other algorithm you're using, and with the gradient boosting regressor, you're getting again, a higher training and a higher testing accuracy. So the training score is around 94.8%, and the testing score is around 91.08%. So these are the two scores that we are getting right now. So we have a model whose training accuracy is 94.8% and whose testing accuracy is 91.08%. So these are the two different accuracy scores that we are getting right now. As you can clearly see, it's a better model. And one of the other key ideas that we talked about in the prior discussion was N estimators. And this is, again, a bit of a technical topic, but at a very high level, N estimators is a kind of a hyperparameter. It's a tuning knob. So every machine learning algorithm will have these kinds of tuning knobs. And you can actually find out what is the optimal value of N estimators to build a good quality model. Okay, so here we are taking N estimators equal to 100, but you can try different values of N estimators. And when you try different values of N estimators, you will see very clearly that the scores will vary a lot. So for example, if you take N estimators equal to 1, the training and the cross-validation scores. Cross-validation is nothing but a testing score. It's an average testing score. So the training and testing scores both will be low. So we saw that yesterday briefly. So if you keep a very low value for N estimators, the model will be highly underfit. And as you keep increasing the value of N estimators, the model will become more and more good fit. So if you have a higher value of N estimators, what will happen is the model will become more and more good fit. So that is the inference that we can get out of it. Okay, so for a smaller value of N estimators, we have a highly underfit model, and as N estimators keeps increasing, we have a more and more good fit model. So that's the inference we can get out of this. We have a more good fit model as we increase the estimators, and we are trying to find out somewhere in between, somewhere here. This is the vicinity where we are trying to find the good fit zone. The good fit zone is that zone where we have the highest test scores, we have the highest validation scores. Okay, because remember, beyond the point, if you continue increasing your N estimators, what will happen? You will reach overfitting. You will reach the overfitting zone where the training will continue to go up, but the testing will continue coming down. You'll reach overfitting. So you're trying to reach the zone where you get the highest validation scores. That is the good fit zone that you're trying to reach.